All right, let's get into it. Today, we're looking at a paper that's making some serious waves in computer vision. It's called BACS, which stands for Background Aware Continual Semantic Segmentation. And trust me, this is way more than just a small tweak on existing methods. It's a completely fresh take on a really thorny problem. How do you get an AI to learn over time when the world is, well, ambiguous? So here's how we're going to break it down. First, we'll get a handle on the core issue, this background shift dilemma. Then we'll unpack the BACS framework and its 4 big ideas. After that, we'll check out the numbers to see if it actually works. And finally, we'll talk about what it all means. All right, first up, let's really get into the weeds of this background shift problem. So to really get this, you have to ask a simple question. What exactly is the background to a model that's learning things one step at a time? I mean, it's not just a blank wall, right? In the real world, the background is a mess. It's full of things the model already knows about, and it's also full of things it has no idea about yet. And that ambiguity, that's the real villain here. It's what causes so many problems. And this whole problem exists in the world of continual semantic segmentation, or CSS for short. The name of the game in CSS is hitting that perfect balance between 2 competing goals. You need plasticity, which is just the ability to learn new stuff, but you also need stability, so the model doesn't just, completely forget everything it learned yesterday. That's catastrophic forgetting. And this whole background issue, it throws a massive wrench into both of those things. Okay, so the paper breaks this problem down into 2 flavors, and this is really the core of it. First, you've got backward background shift. Imagine you've already taught your model to identify a person. Now, in the next training step, you show it a picture of a person on a sofa, but you only label the sofa. Everything else, including the person, gets labeled as background. You're literally telling your model, hey, that thing you thought was a person? Nope, it's background now. You're forcing it to forget. Then you've got forward background shift. This is when objects you're going to teach it about in the future are currently lurking in the background. This just confuses the model and makes it harder to learn those classes later on. Both of these together are just a recipe for catastrophic forgetting. So, faced with this really tricky problem, how do you even begin to solve it? Well, that's where the BACS framework comes in. It proposes a totally new way of thinking about this.
And the big idea behind BACS is that it completely throws out the old way of doing things, which was called pseudo-labeling. See, methods like plop would basically take the old model and have it guess what might be in the background of a new image. But what happens if the old model is wrong? Well, those errors just build up and up over time. It's a classic case of confirmation bias. The model gets more and more confident in its own mistakes. BACS's approach is totally different. It says, forget guessing. Let's just detect the problem directly.
And this detect, don't guess philosophy is really built on 4 key pillars. So let's dive into the technical details of what makes BACS tick. First up, and this is really the heart of the whole system, is the backward background shift detector. Think of it as a special module that has one job and one job only, to look at every single pixel labeled background and ask, hey, have I seen you before? Are you really background, or are you an old class in disguise? So how does it actually work? It's not magic, it's actually just clever geometry. For every class the model learns, like person or car, it saves a kind of signature, a representative feature vector they call a prototype. Then, when a new image comes along, it takes the features of each background pixel and compares them to all the prototypes it has stored. It's basically measuring the distance. If a pixel's features are super close to, say, the person prototype, the detector flags it. It's like it's raising its hand and telling the rest of the model, whoa, hold on. The label says this is background, but it sure looks and smells like a person to me.
Okay, so now you have this detector flagging all these problematic pixels. So what? What do you do with that info? Well, that brings us to the second brilliant piece of this puzzle, a new kind of loss function that's specifically designed to listen to the detector.
Here's the key. The loss function gets the signals from the detector and then adjusts how it penalizes the model. If the detector says, hey, this pixel is almost certainly an old class, not real background, the loss function basically says, got it. It then massively reduces the penalty for that specific pixel. It's like telling the model, you know what? Don't worry about getting this background pixel wrong. In fact, you're right to think it's an old class, so I'm not going to punish you for it. And just like that, you stop the model from unlearning things it already knows. Now, the detector and the loss function are the main 1-2 punch against background shift, but BACS doesn't stop there. It has 2 more tricks up its sleeve to really hair down on catastrophic forgetting. First, we have something called masked knowledge distillation. Now, regular knowledge distillation can be a bit of a blunt instrument. It tries to make the new model behave exactly like the old one, which can stop it from learning new things effectively. BACS is much smarter. It uses the detector to create a mask, and it only applies that stay-the-same pressure on the pixels that the detector has identified as old classes. It's a surgical strike for stability. Then it combines this with Dark Experience Replay, or DER. This is more of a general memory booster. It keeps a small collection of old examples and the model's raw outputs for them, and it just kind of rehearses them every now and then to keep that old knowledge sharp. And for the last piece of the puzzle, BACS makes a really smart architectural change. It tackles the age-old problem of how you physically add new classes to a model that's already been trained.
So the old way of doing this was pretty clunky. You'd literally bolt on a whole new head to the model for each new class. But then you have a huge problem. How do you set the initial weights for that new head? The go-to move was this initialization trick, where you just copy the weights from the background class. The trouble is, this creates a huge bias and makes it harder for the model to actually learn. BACS just gets rid of all that. It uses a transformer decoder with these learnable class tokens. Now when you want to add a new class, you don't bolt anything on, you just add a new token to the set, and you initialize it as the average of the tokens you already have. It's way cleaner, way more efficient, and it completely sidesteps that nasty initialization bias.
Okay, so the theory sounds amazing, right? It's elegant, but the million-dollar question is, does it actually work in practice? Let's look at the numbers. All right, here's the Pascal VOC 15-1 benchmark, which is a seriously tough test. And just look at these numbers. For the old classes, BACS hits 72% MIOU. That's fantastic stability, it's not forgetting. But the absolutely jaw-dropping number is for the new classes. It scores a 44.32%. That is literally more than double what the previous state-of-the-art plop could do. That's an insane jump in plasticity.
And this chart just makes it crystal clear. Overall, BACS is sitting at 65.4 MENA MOU. That's an almost 11-point lead over plop. I mean, in this field, an 11-point jump isn't just an improvement, it's a giant leap. It shows the system has a much, much better handle on that stability-plasticity trade-off.
And this wasn't just a fluke on one dataset. They ran it on cityscapes, and it's the same story. Sure, its performance on old classes is about on par with the others, but look at the new classes again. BACS pulls way ahead, almost doubling the score of its nearest competitor. The takeaway is clear. This thing is just flat out better at learning new stuff without wrecking its old knowledge.
Right, let's bring it all home and recap what really makes BACSes a game changer.
So it all boils down to these four big ideas, right? You've got the detector, which is a brilliant move away from the guesswork of pseudo-labeling. You have the smart loss function that actually listens to the detector. Then there's that surgical use of masked knowledge distillation for stability. And finally, the super clean transformer decoder for adding new classes. Any one of these would be a cool paper, but together they're just incredibly powerful. And this quote from the authors themselves really nails it. It's their whole philosophy in one sentence. Use the detector to figure out what's real background and what's dummy background, and then just ignore the dummy stuff in the loss function. It's a detect, then ignore strategy. So simple, so powerful, and the results speak for themselves. So this leaves us with a really big question, doesn't it? BACS is an amazing solution for semantic segmentation, for sure. But the core idea, this philosophy of actively finding and dealing with ambiguity in your data, that feels like it could be applied almost anywhere. Could this be the secret sauce? Is explicitly tackling the messy middle, all the undefined, confusing parts of the data, the next huge breakthrough we need to build AI that can actually learn for its entire life, just like a person? It's a pretty exciting thought to end on.